Good morning, dear students. Welcome back again with the new lesson of Standard 8, lesson number 15, sound. Now, how is sound produced? Definitely because of the vibration of the waves. Now, production of sound. How actually sound is being produced? We have learned that sound can be generated from a vibrating object. With an example of tuning fork, we will now learn about how a sound is produced due to such vibrations. The photograph of tuning fork is shown in the figure 15.1. A tuning fork is made of two prongs and a stem. Keeping the stem ready, if the prongs are stuck, they start vibrating. Figure 15.2a shows a stationary tuning fork. To show the state of air around a tuning fork, vertical lines are used. Here, the vertical lines are equally spaced. It indicates that average distance between the air molecules is the same everywhere, and the average air pressure in the three regions A, B, C is also the same. If the stem is steady and the prongs are stuck, the prongs are set into vibration. It means that they are set into periodic motion in forward and backward direction. We will see step by step the result of such a motion. If during the vibration the prongs of the tuning fork go away from each other, as shown in the figure 15.2b, the air outside the prong is compressed and the pressure there increases. Such a state of high pressure is created in the region A in the figure. The region in which air is at high pressure and high density is called as compression. And the next step, vibration, the prongs of the fork come close to each other as shown in figure 15.2c. In this case, the molecules near the prongs get more space to move in the region A decreases. Such a region in which air is low pressure and low density is called as rarefaction. So alternate compression and rarefaction is formed when the tuning fork is set into vibration. The compression where density of air and pressure is more, rarefaction density of air and pressure is less. However, the air molecules in this region which is compressed state earlier in figure 15.2 region A transfer the energy to the air molecules in the next region B. So the air in that region goes to compressed state. See figure 15.2c region B. Such a periodic motion of the prong creates compression and rarefaction in the air, and these are propagated away from the prongs. These are nothing but the sound waves. When these waves reach our ear, the eardrum vibrates. Accordingly, specific signals reach the brain and we get the sense of hearing a sound. Propagation of sound and medium. Now, in which direction the propagation of sound is taking place and which medium is essential or whether medium is essential or not in order to transfer the sound. So that can be explained with the help of one small experiment here as shown in figure 15.3, which is written here that medium is necessary for propagation of sound. We have learned that in the sixth standard that sound travels through some material medium like solid, liquid or gas and reaches us. But what if such medium does not exist between the source of sound and our ear? Sound generation and propagation needs medium like air. A simple experiment can prove this. The experimental arrangement is shown in figure 15.3. In this experiment, a vacuum-tight bell jar is placed on a smooth horizontal surface. The bell jar is connected to a vacuum pump via tube. We can remove air inside the bell jar using the vacuum pump. As shown in the figure The bell jar contains an electric bell, when which is connected to the power supply through the lid of the bell jar. At the start of the experiment, vacuum pump is off and the bell jar contains air. If the key to electric bell is now switched on, the bell starts ringing, and ringing can be heard from outside the bell jar. Now, if the vacuum pump is switched on, it starts removing the air from the bell jar. As the quantity of air inside the bell jar decreases, the level of ringing sound heard outside also decreases. If the pump is operated for sufficiently long period, the quantity of air like inside the bell jar will be low. At this point, the level of ringing sound will be very low. This experiment demonstrates that sound generation and propagation needs a medium. If the air inside the bell jar is totally removed, we will be able to hear the sound of ringing bell. Why? Frequency of sound waves. Using the figure 15.2, we have learned about how vibration of tuning fork results in generation of compression and rarefactions in air. More detailed observation and any object, more detailed observation shows that actual variation in air density and pressure are as shown in figure 15.4. If any object vibrates in the air, such sound waves are produced in the air. You can see here alternate compression and rarefaction, because of which pressure is increased and decreased alternately. The cycles of compression, rarefaction and sound wave and a change in pressure is shown in the picture. As shown in the figure 15.4, one compression and one rarefaction together forms one cycle of the wave. The number of cycles formed in the air in 1 second will be decided by the number of times the prongs of the tuning fork or any other vibrating body vibrate back and forth. The number of vibrations of the tuning fork in 1 second. So the tuning fork will help us to decide, the frequency will help us to decide what could be the intensity of the sound. Number of such cycles are produced in the air or other medium per second is called the frequency of the sound wave. The frequency is measured in hertz. If one cycle is completed in 1 second, the frequency is set at 1 hertz. For example, the tuning fork in figure 15.1 shows frequency to be 512 hertz. It means that the fork vibrates 512 times per second. This vibration will get 512 cycles of compression and rarefaction in the air per second. Thus, the sound generated by the fork will have frequency of 512 hertz. The frequency of tuning fork is decided by the dimension of the prongs, length, thickness, and the material used for making the fork.